Hello, my name is Bailey Hill, and this is my very last module for regression. So let's get started. This is my module 3. I wanted to start off with dummy coding um, and note that these categorical variables require special attention regression analysis because unlike the dichotomous or continuous counterparts, they can't be entered just as they are. So they need to be recoded into a series of variables that can then be entered into a regression model. So in my data, I use the GRE as a continuous predictor, which is a non-binary but categorical predictor. And so dummy coding is a way to make this categorical variable into a series of dichotomous variables by recoding. So we then recode them into dichotomous variables, which are variables that can have a value of 0 or 1. So for all but one of the levels of a categorical variable, we can create a new variable that has a value of 1. So an example, D1 here, rank 2 is a value of 1, D2 and D3 have a value of 0. The level of the categorical variable is coded at, that is coded as 0 in all the new variables. So rank 1 here, 0, 0, and 0 is the reference or base level, so that's rank 1, or the level to which all the others are compared. So in this case, 1 is the highest and 4 is the lowest. Moving on into my linear regression. This is a good time to bring up Friedman's point. Although he believes that regression does not carry much, he says that regression can't carry much of a burden in a causal argument, but it can be helpful in data summarizing. And so that's what we're doing now. So he also notes that social science is possible for regression to be used, and conclusions can be drawn from non-experimental data, which is what I have. Moving on into our numbers here. So we have our rank, which is D1, D2, and D3, which is back to our dummy coding as our D1, D2, and D3. 1, 0, 0, 1, 0, 1, 0, 0, 0, and 1. So we've recoded it so that it can be entered into this regression equation as a binary predictor. Our rank order here runs from our constant to 4, so D1, D2, and D3. D1 is 2, D2 is 3, D3 is 4, etc. R squared in this equation counts for 11% of the variance. And then all of our t values here for D1, D2, and D3 are negative, which could be a possible sign of multiclinearity. And then our t value for GRE is extremely high as well. So continuing on, we can reject our null for all of our predictors. Moving on into our histogram, we can note that the histogram is not normally distributed, as evidenced by the normal distribution curve here that is positively skewed. And then onto our PP or probability plot. So we're looking at our expected cumulative probability versus our observed cumulative probability for our admissions. Data is obviously skewed across this line here, especially from 0.4 to 0.7. So yeah, our data is skewed as evidenced here and here. So next I wanted to talk about my logistic regression. So logistic regression, according to Press and Wilson, is usually formatted mathematically by relating the probability of an event to conditional explanatory variables to another variable through a some form of logistic CDF. So that's according to Press and Wilson. So we can begin by looking at the total law probability, which is accomplished by subtracting our natural log, so b, from 1. For our GRE, it's 1 minus 0.004, which is 0.996. So for every point increase in the GRE, score, the odds of admissions increase 0.996. And then for our exponential of the B coefficient, so here our odds ratio rather will tell us if our natural will increase. So for our first dummy code, our rank 1 was 0, 2 was 1, 3 and 4 were 0. So every point increase, the odds of being admitted increased 27.8%. So that would be here. And then for D2, 1 and 2 were 0, 3 was 1 and 4 were 0. And so for every point increase in scoring, the odds of being admitted increased by 1.488 rather, which is here. And then further on for D3, 1, 2, and 3 were 0, and 4 was 1. And then for every point increase in scoring, the odds of being admitted increased by 78%, so or 1.788. The higher the rank, the higher the odds were of being accepted. And then our D1 has a rank 2 coded as 1. So if our rank is 2, an individual has 27.8 chance of being admitted into higher education. Our D2 rank here has level 3 coded as 1. So if our rank is 3, you have a 48% chance. And then if D3 rank has 4 coded as 1, so if our rank is 4, so our D3 rank, the individual will have a 78% chance of being admitted. And then this passes 3 of our assumptions, so the assumption of independent observations, the assumption of 1 or more independent variables, and then our assumption that it is measured on a dichotomous scale. So next, if we take a look at our interaction between our GRE and rank variables, so our second figure here, we can look at and see that GRE by rank 2, so here, produces non-statistically significant results. This is due to rank being lower and then connected to a lower admissions rate. So our only significant results were rank 4 in GRE, which would be logical because the higher GRE scores that an individual have, the higher the probability they will have of being accepted. And so not only is this statistically significant here, but it's more than likely that an individual will have, the higher rank will have higher GPA and high GRE, as well as other factors that will help them be accepted into higher education. So logically, this data set makes sense, especially since we created a data set, or rather we found a data set that was useful in understanding something that was very straightforward, like GRE, GPA, and then rank as well. And so this is my module 3, and it's been a pleasure. Thank you.